Hey everybody. Today we're talking about polynomials. A polynomial is just a function of the form constant times x to a power plus constant times x to a power, etc. The only restriction is that those powers have to be non-negative integers. The highest power that you see in a polynomial is called the degree of the polynomial, and the numbers that are being multiplied by the powers of x are called the coefficients. Let's see a few examples of polynomials. X to the third minus 8x squared plus 4 is a pretty typical polynomial. X to the 17th plus pi x to the fourth is a polynomial. Here we see a coefficient that is not an integer and in fact isn't even a rational number. X to the 9th, this is a polynomial. It just has one term in it. 2 is also a polynomial. Constant functions are always polynomials. In fact, they're the simplest polynomials that there can be. Finally, 2 minus x plus 5x to the third plus 8x to the fourth over 2. Now, this doesn't necessarily look like a polynomial right away. But if we divide that 2 all the way through, in fact, we do get a polynomial. So polynomials don't necessarily have to be initially written in the form at the top of this slide. It just has to be the case that we can write them that way. Here's a few functions that are not polynomials. 3 to the x is not a polynomial because there's an x in the exponent. Polynomials always have the x's in the base. This is an exponential function. X squared minus 7x plus 2 plus x to the negative second. This isn't a polynomial because we have a negative exponent. Similarly, 5x to the 2/3 minus x is not a polynomial because of the 2/3 in the exponent. It's not an integer. 1 over x to the third minus 1 is also not a polynomial. Here we have x's in the denominator. One nice thing about polynomials is that we can add and subtract them and get polynomials back. We do this just by adding and subtracting the like terms. Here's an example. Here are two functions, f and g. They're both polynomials. Let's find f plus g and f minus g. So I'm writing down the formulas for f and g, both in parentheses, and adding the two. Now I'm going to go through and combine like terms. First, I look at the fourth power terms. There's only one here, 2x to the fourth. The third power terms, the x cubes. The function f has 5 of them, and the function g has 1 of them, so overall I have 6x to the thirds. For the x squareds, I have negative 3x squared plus x squared, so negative 2x squared, and so on. For f minus g, the parentheses become a little bit more important. I need to subtract all of the terms in g, not just the leading term. And so when I actually carry out that subtraction, the very first thing I want to do is to distribute the negative sign. Negative 2x to the fourth minus x to the third minus x squared, and so on. Now, as before, I'm combining like terms. Negative 2x to the fourth plus 4x to the third, and so on. Polynomials are fairly nice compared to other functions that we run into in higher mathematics. In particular, the domain of any polynomial is all real numbers. There's never a value of x that you can't plug into a polynomial. Secondly, the graphs of polynomials are always continuous and smooth. There's never any jumps, and there are never any corners. This picture is fairly typical of the appearance of a polynomial. It has a nice smooth shape. The highest power term, or leading term, of a polynomial determines its end behavior. That is, what happens when x gets very, very large or very, very negative. In particular, we need to look at the sign of the leading coefficient, a sub n, and we need to look at whether the exponent there, the highest power term, is even or odd. If n is even and a sub n is positive, then the polynomial goes to infinity in both directions. It has end behavior that's the same as the function y equals x squared. If n is even but the leading coefficient is negative, then the polynomial goes to negative infinity in both directions, like y equals negative x squared. If the degree is odd and the leading coefficient is positive, then the function is going to behave like y equals x. It's going to go to infinity on the right and negative infinity on the left. Finally, if the degree is odd and the leading coefficient is negative, then the polynomial is going to behave like y equals negative x in its end behavior. It's going to go to negative infinity on the right and positive infinity on the left. By the way, notice that this is talking about end behavior only. What happens when x gets very, very large in absolute value? We're not saying anything about what the function is doing closer to 0. By the way, the a sub n, the coefficient in that highest power term, sometimes gets called the leading coefficient of the polynomial. Let's conclude with a short example. Determine the end behavior of this function. F of x equals negative 0.005 x to the fifth plus 0.02 x to the fourth plus 0.135 x to the third minus 0.27 x squared minus 1.08 x. We only need to look at the highest power term, negative 0.005 x to the fifth. So this function is going to behave like y equals negative 0.005 x to the fifth when x is very large or very negative. The power is odd and the coefficient is negative. So we're looking at end behavior similar to y equals negative x. It's going to go to negative infinity on the right and infinity on the left. So let's see the actual graph of this function and see if we're correct in what we've been saying. Yes, as x gets bigger and bigger to the right, the function eventually goes to negative infinity. As x gets bigger and bigger in the negative direction, eventually the value of the function grows towards infinity.